everyone, and welcome back for another deep dive with us. Today we're going to be looking at the relationship between work and energy in physics. And to help us do that, we've got a pretty cool interactive simulation to work with.
Yeah, it's a really neat tool.
It's called Work Done on a Block, with parentheses work energy principle, created by Shazreen. And it basically lets us visualize all these forces and energy changes happening
Mm.
in a way that, just reading it in a textbook could never really do it justice.
Yeah, you can actually play around with it and see the results right there in front of you. It's almost like having your own little virtual lab.
Yeah, exactly. And so,
Yeah.
so this simulation focuses on a block moving across 3 different regions, each of which have their own unique conditions.
You got like a little obstacle course for the block.
Yeah, exactly. So in region A, we've got this applied force pushing the block along, and there's no friction.
So think of it like just giving the block a good shove to get it moving.
Yeah,
That initial push, that's where the work is being done.
Mm.
You're giving the block kinetic energy.
exactly.
The energy of motion.
And then it enters region B, where we remove that applied force, but the surface is still frictionless.
So now it's just coasting along, maintaining that energy that we gave it in the first region.
Right, and it's interesting in region B because, gravity's still acting on it, of course.
Of course, gravity's always there.
But it's not actually doing any work in this particular case.
Right, because the block's moving horizontally
Yeah.
and gravity's acting vertically.
Yeah, they're perpendicular. So for work to be done, the force and the displacement have to be in the same direction.
Exactly.
So then our little block, it cruises along in region B, enjoying its little frictionless ride. But then it hits region C.
And that's where things get a little rough.
Literally. Literally.
So now we introduce friction.
Yeah, that force that opposes motion.
I'm picturing like the block hitting a patch of sandpaper or something. And so it's still moving,
Yeah.
From that initial push in region A, but now it's got to fight against this friction force. And that's where we see this concept of negative work come in, because friction is acting in the opposite direction to the block's motion.
Right.
So it causes it to slow down,
Yep.
lose kinetic energy.
So we've got these 3 regions, each with their own unique set of forces and stuff. But what's really cool about the simulation is the amount of data it gives you. We're not just watching this block move. We get a detailed breakdown of all the numbers.
Yeah, all the nitty-gritty details.
Yeah, the force and the velocity and the acceleration, even the different types of energy involved.
You can see it all laid out right there.
Kinetic, thermal, total energy.
It's like having X-ray vision into the physics of it.
Yeah, it's awesome. We can see exactly how much kinetic energy the block has at any given moment, how much energy is lost due to friction, how that energy gets converted into thermal energy.
Oh, don't forget the graphs. That's one of my favorite parts.
The graphs are amazing.
You get to actually visualize all this data.
Yeah, you've got your displacement versus time, velocity versus time, acceleration versus time.
You name it, it's there.
And then there's separate graphs for each type of energy, plus a combined graph that shows how it all relates.
It's beautiful.
It really is. It's like a data feast. So speaking of the block's little journey here, one of the things that really stood out to me was how this simulation highlights the work energy principle.
Right. That's really the core of what we're looking at here.
So can you remind me again what that principle is?
So basically it states that the work done on an object is equal to the change in its kinetic energy.
Okay, so in region A, the work we're doing by pushing the block, that's what gives it its initial kinetic energy.
Exactly.
And then in region C, the friction is doing negative work.
Right. It's causing the block to lose some of that kinetic energy.
Okay, cool. So this is starting to make a lot of sense to me. But I am wondering, what kind of insights can we get from this simulation that we wouldn't necessarily get from just reading about the work energy principle in a textbook?
Well, that's a great question. And that's where we really start to see the power of this simulation. So stay tuned for part 2, where we'll dive into that.
Awesome. Can't wait. All right, so we've kind of laid the groundwork here, explored this cool simulation a little bit, and how it shows us this work energy principle. So now I'm ready for those deeper insights you were talking about. What can we really learn from this that goes beyond just the, textbook definition?
Well, remember how you were mentioning all that data and those graphs? All that stuff isn't just there for show.
Oh, yeah.
It lets us actually manipulate the variables and see how those changes affect the block.
So, we can tweak the driving force, we can mess with the block's mass.
Exactly. Like, for example, let's say we double the driving force in region A. What do you think would happen to the block's kinetic energy?
Okay, let me think. If the force is stronger, it's doing more work over the same distance. So I'm guessing the block would gain more kinetic energy and would move faster through regions B and C.
Exactly. And you can actually see that in the simulation. Watch the kinetic energy value go up on the graph as you increase the force.
Wow, that's cool.
But here's where it gets even more interesting. Let's say we keep the driving force the same, but we change the block's initial position.
Okay.
What happens if we start the block closer to the end of region A?
Okay, so if the distance over which the force is applied is shorter, that means there's less time for it to accelerate. So even with the same force, it wouldn't gain as much kinetic energy.
Right, because it has less time to speed up.
Makes sense.
And this really highlights that work depends on both force A and E distance.
It's not just how hard you push, it's how long you push for.
Exactly.
I'm really starting to see how this simulation makes things so much more intuitive.
Absolutely. Now let's talk about the block's mass. This is where things get a little bit more complex,
Okay.
but it really shows the depth of the simulation. Remember I mentioned that the creators linked the mass of the block to the friction in region C?
Yeah, that was a really cool detail. Like, it's a built-in lesson about how those two things are related in real life.
Exactly. It's not just random. A heavier object presses down on the surface with more force. So that increases the friction force.
So if we increase the block's mass, it'll encounter more friction and lose kinetic energy faster in region C.
Precisely. Now here's a question for you. If we wanted to keep the block moving at the same speed in region C, even after increasing its mass, what could we do?
Okay, so increasing the mass means more friction, more negative work done by friction. So to counteract that, we need to increase the positive work done in region A. So increase the driving force.
You got it. It's a balancing act between those two forces.
This is so cool. It's like you're actually getting to experiment and test your understanding.
Exactly. Now, one thing that I think often sparks curiosity about this simulation is why they chose to link mass and friction in this specific way.
Yeah, I was wondering about that too.
It's an interesting choice.
Like, it seems very deliberate.
It is.
Yeah.
It's important to remember that simulations are simplified models of reality.
Right, they can't capture every single detail.
And in this case, they likely chose to link mass and friction to illustrate this fundamental principle that heavier objects tend to experience more friction.
Okay, that makes sense. Like pushing a heavy box across a rough floor versus a light one definitely takes more effort to keep that heavy one moving.
Right. But in the real world, the relationship between mass and friction can be much more complex. It depends on the surfaces, the presence of lubricants, even things like the temperature and humidity.
So the simulation gives us a good general understanding, but it's not always going to perfectly reflect every real-world situation.
Exactly. It's important to keep that in mind when you're using simulations.
That's a helpful reminder. I'm seeing this simulation as more than just like a fun interactive tool. It's also a way to think critically about how these concepts apply in real life.
That's the kind of thinking we want to encourage.
This has been so insightful. We've explored these interactive elements, looked at the relationship between mass and friction, even touched on the limitations of simulations.
And we haven't even gotten to those real-world examples yet.
I know, I can't wait. But before we jump into those, there's one more thing I've been wondering about the simulation itself. You mentioned that gravity isn't doing any work in this scenario because it's acting vertically and the block's moving horizontally. But what if we changed that?
You're thinking ahead.
What if we introduced a ramp into region B?
That's a perfect segue into our next topic, the inclined plane. How would that change the forces at play and the overall energy dynamics?
Okay, so this inclined plane idea, I'm really intrigued by this. We've been talking about how gravity doesn't do any work on the block when it's moving horizontally, but like you said, adding a ramp just throws a whole new element into it.
It really changes things up.
Yeah, so walk me through this. Let's say we add a ramp into region B. How does that change things for our block?
Well, now, as the block starts going up that ramp, gravity is not just pulling it straight down anymore. Part of that gravitational force is now acting parallel to the surface of the ramp.
Oh.
So it's directly opposing the block's motion.
So it's like gravity's kind of working against it now, trying to pull it back down the ramp.
Exactly. And that means that now gravity is actually doing negative work on the block as it's moving up the ramp.
Okay.
It's fighting against gravity.
So the block's going to slow down as it climbs up the ramp, losing kinetic energy. Does that energy just like disappear?
Well, that's where this other type of energy comes in, gravitational potential energy.
Right.
As the block moves higher up the ramp, it's gaining potential energy.
Okay.
It's like storing up energy that can be released later on.
Okay, so like I'm picturing a roller coaster, slowly going up that first big hill. It's losing speed, but it's gaining potential energy.
Right.
That's going to be unleashed as it goes down the other side.
Exactly. A perfect analogy. The higher the block climbs, the more potential energy it gains.
Cool. So then what happens when the block reaches the top of the ramp
Mm-hmm.
and starts going downhill?
Well, then the situation reverses. Gravity's no longer working against the block. It's now working with it, pulling it down the slope.
Oh.
So now gravity is doing positive work, causing it to speed up, gain kinetic energy.
So that potential energy is being converted back into kinetic energy, like free energy.
Well, not exactly free. It's more like a trade-off. The block had to use up some of its kinetic energy to climb the ramp in the first place.
Right. Okay.
But yeah, it's a great example of how energy can be transformed from one form to another.
This is making the work energy principle so much clearer. It's not just about forces in motion. It's also about how energy is being exchanged and transformed within the system.
Exactly.
And of course, we can't forget about friction, which is still acting on that ramp,
Always there.
opposing the motion.
Yep. Converting some of that energy into heat.
It's like that constant reminder that we can never achieve perfect efficiency. No matter what, some energy is always going to be lost because of friction.
Exactly.
So with this inclined plane example, we've kind of added another layer of complexity to this whole thing, with gravity now being a lot more dynamic. What are some of the key takeaways here that we should keep in mind about the inclined plane?
Well, I think the main thing is, it really highlights the importance of the direction of the forces. When we're talking about work,
Okay.
gravity can actually do positive work, negative work, or even zero work, depending on which way it's acting relative to the object's motion.
So it's not just about whether the force is there or not. It's about how it's acting on the object.
Exactly. And secondly, the inclined plane really shows us how energy can be transformed. Between kinetic and potential forms,
Right.
the block is storing potential energy as it goes up and then releasing it as it goes down.
Like a constant give and take between those two types of energy.
Precisely. And then finally, the inclined plane reminds us that friction is always a factor,
Right.
even when gravity's helping the motion along.
Even when it's doing positive work.
Some energy is always going to be lost because of friction.
No matter how steep that ramp is. This has been awesome. I feel like we've really gotten a much better understanding of the work energy principle. We went from this simple simulation of a block on a flat surface to understanding how things like inclines and gravity can make it way more complex.
Yeah, it's been a great exploration.
It really has. And to all our listeners out there, we hope this deep dive has given you a new way of thinking about the relationship between work and energy. It's a fascinating topic. And until next time, keep exploring and keep asking questions.